We've seen that when a solution is not ideal, it does not obey Raoult's law, which means that in such a case, so a non-ideal solution, we cannot simply write that the vapor pressure, say for component 2, is equal to its mole fraction times its pure vapor pressure. All right, so obviously this would not be true for component 1 either. All right, so these two things no longer hold, and we've seen, in fact, I've drawn over here a case for a non-ideal solution that typically there is a bulge one direction or another. The one I've drawn here is for a positive deviation from Raoult's law, but we can also have negative deviations from Raoult's law. But that as the mole fraction approaches 1, we see behavior that is more and more like Raoult's law behavior. So we can say, for example, that as x, and I'll say x sub j, so it can apply to either the component 1 or component 2, approaches 1, that the vapor pressure of that component is going to approach its ideal vapor pressure. Okay. So as x goes to 0, however, something different happens. So in that case, we still have roughly linear behavior, and I'll draw this in red to emphasize it. We still see roughly linear behavior like this, but it's no longer commensurate with the variation that we would have seen with the vapor pressure of the pure substance. All right, so it's linear and it has some slope, but that slope I'll just say is equal to k, and I'll specify that a little bit more. But it's going to be different, for every substance that we have in a mixture. So, for example, it's going to be different for, I should probably put a label on here, it's going to be different for the two components of this mixture. All right, so that slope is going to depend both on the composition of the mixture and of all types of both compositions. So what we find in this case is that we see that the vapor pressure for component J is actually going to go as the mole fraction times this slope. And so for a case of component 2, as I've drawn here, it would be the mole fraction of 2 times a particular constant that is specific to that component and also specific to this combination of components. All right, this particular constant that we've put in here is something known as the Henry's law constant. Okay, and as I said, it'll be different for different components. It'll also be different for different mixtures. All right, so we can also equally well write that P1 goes to x1 kh1. But now, mind you, this is in the limit of x2 going to 0, and this is in the limit of x1 going to 0. So what I've drawn here is x2 going to 0 at this end, because I've got x2 as my horizontal coordinate. For x1 going to 0, it would be at this end of the curve, and I haven't drawn that for you. So I'm focusing on K2 for now. All right, so as these solutions are nearly ideal, so I'll say for a nearly ideal solution, what we would have is that this Henry's law constant for both of the components is going to approach the pure vapor pressure for those components. That is to say, we're lying closer and closer to this line that represents the ideal line, the Raoult's law line. So when it is not ideal, however, we find that the Henry's law constant is never equal to this pure vapor pressure. Now, can we draw some distinctions about this? We've talked about both positive and negative deviations. For a positive deviation from Raoult's law, and that's the one that I've drawn here on the left, what we generally find then is that the Henry's law constant, and I'll leave that general for component J, is going to be greater than the vapor pressure of that pure substance. Similarly, for a negative deviation, what we'll find is that the Henry's law constant is less than, I'll draw it over here a little bit, Henry's law constant will be less than the vapor pressure of the pure substance. Now, I want to get a handle on what's going on here, and I'm going to make a claim that I hope you will accept, and that is that when one of the components, in this case I'm showing component 2, when one of the components approaches Raoult's law behavior as it approaches 1, so as x2 goes to 1, and the vapor pressure of that component, I should say 2, approaches the vapor pressure of the pure component, what we find is that the Gibbs-Duhem equation actually guarantees that the other component will follow the Henry's law in that same limit. Now I'm going to do this for x1 going to 1. So we're talking about the limit of x2 going to 0 because I want to focus on this part now of this graph. So this will be my condition in this case. But let's see what the Gibbs-Duhem equation has to say about this particular variation. So remember, the Gibbs-Duhem equation basically says that if I take the mole fraction of 1 times the change in its chemical potential and add that to the mole fraction in 2 times the change in its chemical potential, I should get 0. All right, these two chemical potential changes are interdependent upon one another. Now, I also can write for, in general, for the jth component, that it's equal to the chemical potential of the pure substance, not writing very well today, plus RT times the log of its vapor pressure. Now, technically this is vapor pressure over 1 bar, but I hope you'll allow me the shorthand of just writing it this way. All right, so when I do the differential of this chemical potential, because I'm going to need it in here and here, I'm going to assume that temperature is constant, so this does not vary. This is constant, so that doesn't vary. So the differential of the jth component is simply going to be RT times the differential of log Pj. All right. Now, for this component, as x goes to 1, P1 is going as x1 P1 star. So the log of P1 would be equal to the log of x1 plus the log of P1 star. So the differential of this, the differential of the log of P1 with respect to x1, and we'll say at temperature and pressure constant, that this is simply going to give me the differential of log x1, which is 1 over x1. All right, so now when I take this result and I put it into the Gibbs-Duhem equation, so now I'm going to go from here, and let's change color just for variety. What I'll have is x1 times the differential of mu, which I've basically worked out over here, is just going to be 1 over mu1, 1 over x1, and I'll have a dx1 at the end here. I think I left that out here. I should have dx1 out here. Okay, so this differential will turn into this, and the differential for 2 is what I'm trying to determine, but I can give it essentially as d log P2 dx2 at constant temperature and pressure dx2. Okay, so this is equal to 0. Now you'll notice I'm missing factors of RT. I have divided through this equation by RT because I've got an RT over here and I've got an RT over here. It's all equal to 0, so I can divide through by RT and that vanishes. I'm going to make a second declaration, and that is that when I change the mole component of 1, mole fraction of 1, I'm changing the mole fraction of the other. Remember, the two mole fractions add up to be equal to 1. So that means that changing mole fraction 1 plus mole fraction 2 has to change by 0. So in other words, dx1 is equal to negative dx2. So I'm going to plug that in here. What I'll end up with is a negative 1 because these two things will cancel. Negative 1 times dx2, I'll put that over on the other side of the equation. So I'll end up with dx2 times this differential, dp2 dx2, at constant temperature and pressure, dx2 is equal to dx2. Well, okay, this is the same on both sides, so I can basically turn this into 1 over here. And now I can rearrange this equation a little bit to essentially write down d log p2 is equal to dx2 over x2, because I'm going to be dividing by x2 from here, which when I integrate this, I'll end up with an equation that looks like log p2 equals log x2 plus an integration constant. I'll just call that k. All right, well, when I rewrite this in terms of, undo the logarithms here, what I'll end up with is an equation that says that p2 as a function of x2 is going to be equal to x2 times e to the k, but I can just make e to the k be another constant, and in this case I'm going to make it be the Henry's law constant. So you can see that the net result of this is that we get Henry's law by starting with this condition over here, that x1 goes to 1, its vapor pressure is going to go as Raoult's law, and then by using the Gibbs-Duhem equation we can show that the other component must follow Henry's law. Now I haven't been very coherent, I think, in giving this proof, but I hope that you can review these steps and convince yourself that it's legitimate. But what it's basically saying, the bottom line here, is that Henry's law is completely a natural result of the gas approaching a Raoult's law sort of solution at its upper end. As it goes to 1, it's going to approach Raoult's law. As it's near 0, it's going to approach something else, which we'll call Henry's law. And those Henry law's constants just represent the slope of this line that we've drawn here in the diagram.